All right, let's look at the basics of oxidation and reduction. Well, in order to understand oxidation and reduction, you must understand oxidation states. So let's review that first. Remember, oxidation states are also called oxidation numbers or charges. Atoms, when they're in their elemental form, always have an oxidation state or oxidation number or charge of 0 because they're already neutral. Where do you find oxidation states? Right here on your reference table. When elements are combined in a compound, the oxidation states will add up to 0. Like in this example, the oxidation state of Na plus the oxidation state of F will add up to 0. We look them up, we plug them in, and yes, it's true. Same for this formula, but since there's a subscript, 3 times the oxidation state of lithium plus the oxidation state of phosphorus will be 0. And since phosphorus is a nonmetal and it's the last thing in the formula, we use the first oxidation state. So we plug those numbers in, we multiply out, we combine like terms, and voila. Remember that sometimes we have to figure out the oxidation state. So we set up the equation, but we don't know which one for S, so we plug in what we know, we multiply out, we combine like terms, and then we add 6 to both sides, and we get the oxidation state, okay? Also, what you should remember is that electrons are negative. So when you lose electrons, you end up being positive. And when you gain electrons, you end up being negative. So what's oxidation? Well, remember Leo, losing electrons, or oil. So oxidation is loss of electrons. What is going to be ridiculously helpful is if you sketch a number line. So if I lose electrons, okay, so I have to remember that electrons are negative. If I lose electrons, which way am I moving on this number line? That way. So moving that way on a number line indicates oxidation. So what we say is the oxidation number is increasing because as we move this way, the numbers get bigger. So again, looking at a number line, right? Oxidation moves this way. That means the oxidation number increases with oxidation. So what is reduction? Well, remember the GER, gain of electrons, or the RIG, okay? So looking at a number line again, okay? Which way would we move on this number line if we were gaining electrons? Yep, we would go that way. So moving that way on the number line shows a gain of electrons. So what would happen to the oxidation number? What is happening to these numbers as we move this way? Yes, the numbers are going down. So reduction is a gain of electrons, right? We move this way on the number line. So that means reduction is a decrease in the oxidation number. Now, also, as a fun little fact, the arrows point to the side of the reaction that the electrons will be on. So see how the oxidation, the Leo arrow is pointing this way? That says, hey, the electron should be on this side of the equation. And see which way the GER or the reduction arrow is pointing? It says, hey, the electrons should be on that side of the equation. So what do I mean? Let's look. So if I have this, I've whatever formula is there, but I have reactants and products, and I see electrons on this side, okay? Well, look at this again. Which side? Oh, look, pointing over here. So that would be the loss of electrons or oxidation. So when electrons are with the products, it shows loss of electrons or oxidation. On the flip side, if I have the electrons over here, looking back at here, oh, pointing to this side, it's gain of electrons. So if I have electrons on the reactant side, that shows I gained them. I had to add them in, right? Okay, remember this? One way to remember oxidation and reduction is Leo says GER. Lose electrons oxidation, gain electrons reduction. Another way to remember this is OIL RIG. Oxidation is loss, reduction is gain of electrons. All right, it's time to look at some examples. Are you ready? One way to identify oxidation and reduction is by looking at how the charges change. So are you ready to check that out? Okay, here we have a reaction. We have a polyatomic ion, so to see the SO4, well, we can find that charge on table E. So I know automatically what that is. So I'm going to look at what's present. I have zinc, Zn with no charge. I have Cu +2. How do I know it's +2? Well, I already looked up SO4 on table E and I found out it's -2. And if one Cu and one SO4 completely balance, okay, there's the charge. Same idea for Zn. And then I have copper with no charge. Let's label the charges in the equation. That makes it a little easier. So I just looked them up, right? There we go. Why is this Zn over here 0? Because it's an element by itself. Same for this copper, okay? Now, our next step is to eliminate any spectator ions. Say what? Wait, what? What is a spectator ion? Well, it's an ion that's present on both sides of the equation, so it doesn't change oxidation states. So the spectator ions, yes, go, yes, they're just watching. They aren't doing anything. They aren't changing oxidation states. So let's look back at our equation. Are there any spectator ions? Yes, there are. So let's cross them out. Do you see the spectator ion? Right there and right there. It looks exactly the same on both sides. So now let's rewrite it without the spectators. This. Well, that's a lot simpler. Okay, so let's look at each element separately and find out what happened to the charges. So how did they change? So are you ready? Okay, here's the first one. We're going to look at Zn. And I'm going to remember this. So what I'm going to do every single time I have one of these questions is I'm going to sketch this. Now, I could sketch it one time on some scrap paper and keep looking back at it, but I don't want to answer these questions without this, okay? So let's look at Zn. On the reactant side, it was 0. On the product side, it is +2. So how many electrons did it lose or gain? How do you figure that out? Like how many hops, how many spaces on the number line? 2. Watch. 1, 2. 2 electrons. Is it oxidation or reduction? Well, let's look. Which way are we going? We're following the Leo arrow, so it is oxidation. When we say what substance is oxidized or reduced, it has to be the thing that was on the reactant side. So Zn with no charge, just Zn the element, is the thing that's oxidized. Okay, now let's look at copper. On the reactant side, it's +2. Find that on the number line. On the product side, it's 0. Find that on the number line. How many electrons are lost or gained? So how many hops? 2, again. Is it oxidation or reduction? Well, which way are we moving? Okay, so it follows GER, so it's reduction. I know it's reduction, and when we say what substance is oxidized or reduced, it has to be on the reactant side. So that means I have to say that Cu with a 2+ charge is the thing that's reduced. Now, another way to identify oxidation and reduction is by looking at what side of the equation the electrons are on. So let's look at this first one right here, this one. See the electrons? Which side of the equation are the electrons on? Well, they're on the product side, points this way, so that means it shows oxidation. And the thing that is oxidized has to be on the reactant side, so that's H2. So let's look at the next one. There's my electrons. Where are they? On the reactant side, this way. So that shows reduction. And the thing that's reduced has to be on the reactant side, so that's F2. Now, just to confuse you, here are a couple more terms. So we talk about oxidizing agents and reducing agents. Great, fantastic. Ugh, okay, let me try and explain. Reverse, reverse. Okay, if a substance is oxidized, reverse, reverse. It's the reducing agent. If a substance is reduced, reverse, reverse. It's the oxidizing agent. So I like to kind of try to make things make sense in my brain, and this is the way I do it. So for this one, I think about this. Agents don't actually do the work. So when an actor has an agent, the agent's not the one doing the acting, right? But they do set up the work. So reducing agents set up reduction. Well, reduction, remember, it means gaining electrons. So in order to gain electrons, there had to have been some electrons lost already. So oxidation. So the agent sets it up, okay? So the reducing agent sets up reduction by doing oxidation. And the oxidizing agent sets up oxidizing by doing reduction, okay? So the reducing agent is the thing that is oxidized. The oxidizing agent is the thing that is reduced. And when I think about it in terms of like actors and agents, it helps it make sense. So again, whatever is reduced is the oxidizing agent, and whatever is oxidized is the reducing agent. So let's practice. Ready? Okay, so have this whole reaction. Which is the reducing agent? So here's what I want you to do every single time. 0, 1, -1. I probably don't need to go more than this. Draw the number line. Okay, what else do I want you to put? Leo. And this way, GER. Okay, so let's change to our highlighter. Let's do purple. So here is Fe. It went from +2 to this, which is no charge. So it went like this. Okay, so that means this Fe is reduced, which means it is the oxidizing agent. Okay, let's switch colors. Let's do green. So zinc went from 0 to +2. So it went this way. So it was oxidized. It is the reducing agent. Now notice everything I'm referring to is on the reactant side of the equation. Okay, so my question now, I could just do that really quickly. Which species acts as the reducing agent? Well, right here. I just figured it out. Here's another one. So what do I want you to do first? Number line. 0, 1, 2. -1, -2. Okay. Arrow for what? On the top, going this way. Leo, this way. GER. Draw that every time. make it easier. So let's go back to my highlighter and let's start with blue. Cu starts at 0 and goes to +2. So it goes this way, follows the Leo arrow. It is oxidized or the reducing agent. Let's switch colors. We will go light blue. So silver goes from +1, 0. So it goes this way. So that is reduction or the oxidizing agent. And again, remember, notice everything I'm referring to is on the reactant side of the equation. So which one was the oxidizing agent? Right here. So do you see how just taking a moment and figuring it out will just make it easy to get the answer? So how do we identify redox reactions? Let's go over a couple ways. One, look for single replacement reactions. So we have a single element on each side of the equation that is an element neutral, no charge. So see, neutral, neutral, but different elements on each side. Neutral, neutral, different elements on each side. Neutral, neutral, different element on each side. Okay. Look for elements that change oxidation states. So you can go through and figure them out. Well, I know that if I had an element that had no charge and on the other side it's in a compound, well, its oxidation state had to change, okay? So you can go through the equation and look for oxidation states that change, and those are just some examples. All right, so let's try. Which one is a redox? So I'm going to scan. Do I see anything that has single elements? Because that's the easiest way. Oh, I see right here. Well, I see 2 single elements, not 1. But let's look on the other side. In a compound, in a compound. There we go. That one was easy. Okay, looking for single elements is, trust me, the easiest way to find it. And let me just show you this one, why this one for number 4 is not a redox. Remember spectators, the things that were in compounds on both sides, we cross out? Watch this, NO3, NO3 in a compound. AG, oh, AG in a compound, AG in a compound. Cl in a compound, Cl in a compound, Na in a compound. Hold up, I literally cross out everything. There's nothing left to be oxidized or reduced. All right, let's look at this example, okay? So let's look again. Let's follow that strategy. We see spectator. So let's look at this first one. Okay, is it in a compound on this side? What about Cl? Yep. What about Na? Yep. What about SO4? Yep. So it can't be that one. Nothing changed. Okay. Now I see this one, single element, different single element. Oh, I like the sound of that one, right? So redox reaction, okay? And if we look at this last one, everything is going to be a spectator. Now, it looks a little weird, so let me show you. Mg is easy to spot. NO3, easy to spot. And you're like, well, what about the H and the OH? Well, water is really H connected to OH, right? So nothing changed. So the one that is redox. And that is an overview of oxidation and reduction. So that was a lot. I hope you learned something. Hope it made things a little bit less fuzzy. All right.